communication with his startup, Shori. And well, ladies and gentlemen, here we have Mr. Sabir Bhatia for you, and he will take on the camera.
Thank you. I'm waiting for my co-panelists. I don't know why they're not coming on stage. Guys, please join me. So first of all, thank you all for being here today. We have a wonderful panel for you. We have the giants of quantum computing over here from various companies. On the farthest left is Tiecon Nayak. He's a fellow at Microsoft, and he was with the quantum program since day one. Before that, he was a professor of physics at UCLA. And he got his undergrad from Harvard. So please welcome Tiecon Nayak.
Thank you very much. Thanks for the kind introduction. Glad to be here.
To his right, we have Arvind Ratnam, and he's with Q Controls, which is a company that is working in quantum computing and quantum sensors, and very exciting stuff. I had a chat with him before we came on stage today, and you will get to hear some amazing stuff that nobody in the world is doing. And to my immediate left is Jerry Chow. He's a fellow at IBM, and he's a quantum fellow at IBM, and he's involved in, once again, quantum computing effort of IBM. So thank you all for being here today. So, I am no expert in quantum computing. I'm just a person learning just like you are. So I'm going to ask them some very basic questions so that I can understand what quantum computing is all about, and so that we all learn from all of the wonderful research that these three gentlemen are doing. Jerry, let me begin with you. What is the simplest way to define what quantum computing is, and how is it different from classical computing?
You got it. Yeah, thank you very much for that question. And I think it's a good way to start this panel, because I think everybody's probably heard a little bit about quantum computing, but what is it really, right? And in the end, it's a fundamentally different way of performing computation, and it relies on the laws of quantum mechanics, right? So it definitely has its roots in physics. But it involves also these concepts that you might have heard of: entanglement, quantum superposition, quantum measurement. But all in all, what happens is that with these different types of rules, you can treat information entirely differently. And there's a rich mathematical structure behind it all that lets you actually solve and tackle specific types of problems way more efficiently than you could with classical computing. And in fact, for some problems in which you never solve classically.
Wonderful, thank you so much.
And just building a little bit on what Jerry said, the ideas of quantum computing date back to Richard Feynman, early 1980s, 1981. And he was thinking about the following problem, which is, I want to simulate a quantum system. How do I do it on a computer? And he pretty quickly realized that even a modest-sized quantum system, which means a modest description of nature, would require an unbelievably large, exponentially large classical computer. So he said, this is just a no-go. So we need to make the underlying computing machinery operate according to the same laws of nature that the world does, right? And not just the simplified zeros and ones, but take into account superposition of 0 and 1 and entanglement. And so he then showed that you could actually efficiently simulate quantum systems. And then that promptly went nowhere, for about a decade. People knew about it, but it was kind of an oddity until Peter Shor did two things. He discovered his algorithm, which showed that you could factor large numbers and therefore potentially break RSA, which got a lot of people excited, both in good and bad ways. And then a year later, proved that you could do error correction, because I think one of the reasons that people didn't get so excited about Feynman's original work was they thought, well, this looks like analog computing, and we know analog computing has a problem that it's not fault tolerant. and you can't really do error correction, and so you're not going to be able to really compute with it, and so accurately with it. And so those two things that happened in the 90s, really in some sense on the theoretical side, theoretical physics, theoretical computer science, kicked off, a wave of work, and depending on how you count, we're in like the second or third wave of it right now.
Yeah. And one thing, if I can add, if you look at the last 75 years of compute, maybe 70 years of compute, sure, there have been different form factors in which compute can be accessed, etc. But this represents a new way of doing compute, and it is fundamentally a breakthrough for humans. It is something almost equivalent to the Manhattan Project that happened. So what we're onto is something very big.
So, is the hardware approach towards quantum computing same in all of your different companies, or have each of you taken a different way of approaching the whole, quantum computing, I should say, massive step forward?
Yeah, so I think there's actually different ways that people have been fundamentally building quantum processors, and the unit of computation in here is really the quantum bit or qubit. And there are different physical instances to build this. At IBM, we actually use superconducting qubits. They're based off of superconducting circuits, using superconducting materials that need to be cooled down to extremely low temperatures. So many of you might have seen what a quantum computer looks like, at least from IBM, is these, it looks like a chandelier. It's something that actually cools down to 15 millikelvin, right? So many orders of magnitude colder than it is in outer space. And the reason why we need to get them that cold is that for these rich quantum effects to emerge, they need to be that low temperature. And so that we can, to Chetan's point earlier, is like bring down the noise to a level that we can effectively actually use these for information processing types of tasks. Right? So there's a lot of work that's been going through there. At IBM, we're today at the scale of hundreds of qubits within a quantum processor that can be cooled down. We're actually coming up on our 9th anniversary of first putting these systems on the cloud. Actually, this Sunday is the 9th anniversary of doing so. When we started doing this, it was 5 qubits on the cloud, and today we have multiple systems of 100 plus qubits, all actively used by a large community of users around the world today.
Yeah, no, what Jerry said is right. There are many different ways of making qubits. I mean, and actually that's true even of classical computers, right? From a purely, computer science or information theoretic perspective, actually vacuum tubes and transistors are equally good. You can work with either one, and people have made classical, processors with gallium arsenide. There are gallium arsenide processors as well as there are silicon, right? So there are, I would say there's even greater diversity today in quantum processors. People make them with trapped ions, some of the earliest ones, where you strip an electron off of an atom like ytterbium, and you have an ion. It's now charged, and so you can trap it from its charge above some electrodes. And you can make those ions interact with each other. You can effectively, even though the machine sits at room temperature, you can effectively cool this thing down to very, very low temperatures by tricks like laser cooling and so on of the ions. And people do this also with neutral atoms. They're not charged, but you trap them with laser beams and move them around, get them to interact with each other. As Jerry was saying, they use superconducting qubits, so they work with materials like aluminum when cooled down to very, very low temperatures. Go through this remarkable transition to superconducting state, and you can make Josephson junctions with them, which is a kind of nonlinear circuit element. So we are making topological qubits, which is based on a new state of matter, also based on superconductivity. I think there's also spin qubits, which in some ways are closest to classical. But so there really are, very, very different physical instantiations of qubits right now, and they all have different, strengths and weaknesses, and people make choices right now, and let's see. It may be in the future that we'll find that for some applications, some are better than others. Maybe you may end up using a less expensive one for certain applications, and maybe one that's more expensive for others. Let's see. Jury's still out.
So, what kind of problems are ideally suited to be solved using quantum computers that you cannot solve using classical computers.
Yeah, I think.
I think any of us can go. So there are certain, I don't want to get deep into mathematics, but there's certain classes of problems that lend themselves really well to quantum computing. One class is these combinatorial optimization problems. A lot of you who have looked into quantum computing know this well, but normal computers are great at multiplying, but they're not great at factorization. So any sort of optimization, a great example is, let's say you've got 40,000 Walmart trucks that need to deliver 10 million packages to 100,000 households. What's the most fuel efficient route you can take? So this is the classical traveling salesman problem. If you pose this to a supercomputer, it's going to not be able to solve it for I don't know how long, but a quantum computer is typically very efficient at these types of problems. So this is just one example, but just zooming out, these types of optimization problems are found in all kinds of domains, from transportation to even financial, like derivatives trading and such. And people believe, or at least it's popular opinion, that some of the earliest use case applications for quantum computing will be in the fields of chemistry, pharma, which is very, very closely related, as well as in finance. And then you will have probably the second wave, which includes industrial transportation, aerospace and defense, and so on and so forth.
So Samir, I think your question, the way you phrase the question, actually makes an important point implicitly, which is quantum computers aren't going to replace classical computers, right? It's not the case that in 10 years everyone's going to throw away their PCs, we're going to get rid of all the data centers and everything's going to be quantum. They are part of a bigger picture, which is still going to, today we have CPUs and GPUs, we'll have QPUs, quantum processing units. For a typical customer, they may not even know what's underneath the hood. They care about a solution, right? Whether that somehow that problem is divided between some CPUs and GPUs and QPUs, you probably don't even care as long as you get a high quality answer. But it would be what's that?
In the cloud,
in the cloud somewhere, right? It is sitting in the cloud somewhere.
Yeah.
But what I think we can say confidently is that what the QPUs will enable is a classical problem that you would not even try, with today's technologies. And I think it's exactly the things that Arvind just mentioned.
And some of this stuff is already starting to happen, right? Like I think, does everyone know what people use high performance computing for today? A lot of it is driven towards molecular simulation and understanding how electrons are configured and so forth, which has tremendous impact for materials development. And in fact, a majority of the high performance computing clusters today are basically tapped out on a relatively small sizes of molecules. And we're already starting to couple that with quantum computing solutions so that we can open the aperture and solve more. So we've actually been working with partners in Japan. One of the top 50 supercomputers out there, Fugaku, with our partners at RIKEN, to actually study the world's largest chemical molecule ever simulated on a quantum computer, iron sulfide. And we're starting to see that balance of how much supercomputer you use versus how much quantum compute can you use, and how do they really start to piece together, like Chetan mentioned, where in the future you're not just saying I'm going to pick a quantum computer for the full solution. You're picking compute in general, and you're going to get some part of the problem solved on your classical, some part on the GPUs, and some part on the QPU.
Thank you very much for that wonderful answer. Now I'm going to ask Arvind something which I just learned in the room, and he's working on some really amazing use of quantum sensors to create a GPS system without the use of GPS, right? So explain that to us.
Yeah, see, when people talk about quantum computing is one modality of quantum. There's quantum cryptography, then there's quantum sensing, there's even quantum materials. You start thinking about how you build stuff with. Referring to quantum sensing, look, at the end of the day, quantum is all about manipulating things at the atomic level. It turns out that you can use some properties associated with the atom to make exquisitely sensitive and very, very stable sensors. A great example is, let's say you're navigating on a plane. Today, if a plane loses GPS, you may ask, how does a plane lose GPS? It's common knowledge that you can go on eBay and spend a few $100s and buy a GPS jammer. For several thousands, you can buy, it's probably illegal, I'm not even sure. A military grade jammer that you can take out GPS in literally zones, geographic zones across the world. So then what happens with these, it could also be ships, but what happens on these vehicles that rely on GPS is they fall back on what are called as inertial sensors, magnetometers and accelerometers that you also see them in your phone when you use the Compass app, but what we use there is a much higher grade, but those are susceptible to drift over time. So a ship that's drifting in the open oceans, if the GPS is denied, if you use the inertial sensor as a backup, after 8 hours of drifting, you'll be within 1 nautical mile of where you think you might be. That's the approximate error that you'd expect. But using a quantum sensor, using specifically what's quantum navigation, I can be within that 1 square mile after 1,500 hours. So imagine the Titanic sub that sank, and even 1 nautical square mile of water is a lot of water. But now, just coming to a more practical aspect of it, GPS jamming incidents are happening all over the world, especially in current days of geopolitics. There are several zones across the world that are very, very susceptible for jamming. And it's possible to build these devices. There's only a few companies in the world that can do it, and we are one of them. We just announced publicly we are funded by Lockheed and Airbus in this effort. It's possible to build these devices that provide this backup to GPS that will allow you to navigate without GPS. This, unlike quantum computing, there's no hype, there's no scientific risk. It's now turned into an engineering problem, and we are amongst the forefront of this industry. And stay tuned for more updates.
Fantastic, thank you.
Yeah.
Do you see any, in the next few years, any moment that will be, that quantum computing will achieve that kind of escape velocity, or that you're trying to solve some fundamental problem that will cause it to just suddenly become widely used and widely accepted? Or is this more of a, we're going to block and tackle and slowly build upon quantum computing till, it starts solving, fundamental problems in nature?
So my feeling is that it's not going to be a sudden transition. I think that there's going to be, we're already in some sense in this world where there are problems that a quantum computer can solve that a classical computer can also solve, right? The quantum computer might just make you think about the problem in slightly different ways and lead you to or there could be situations in which, the answers are, equivalent, but the quantum computer gives you a slightly different answer. So I don't think it'll necessarily be that kind of sudden thing where you wake up one morning and quantum computers are better than classical computers now, we need to all switch. I think it will be a gradual process. I think there are problems already where quantum computers have given us some insights into the problems we wouldn't have otherwise had. And so I think we are kind of in that transitional period right now. I think there certainly is going to be a point at which quantum computers will be solving problems that we wouldn't even try with classical computers, right? I think there will be a point where, for instance, RSA will no longer be viable, right? And so we need to work now. It's not the next year or two, right? It's probably not even in 5 or 6, 7 years, but it's out there somewhere. So that's why we need to go to post-quantum crypto now. We need to be prepared. There are crypto systems that are safe to quantum attacks. We have some of them that we know quite a bit about. We need to make those transitions now because you don't roll that out overnight. That happens over time. So there are. I think if you look out in the future, there are some kind of very clear, sharp, binary moments where the world changes, and we need to prepare for those. But in the meantime, I think it's much more of a gradual evolution.
So the chat GPT moment that people are waiting for quantum will happen probably over a period of time. But there is unlike other fields, quantum has a curve to it. And that's the reason why this is on the agenda of every CXO or major CXO, because they need to get prepared for the revolution, train their people, etc.
So let's talk about you hit upon an interesting note. This modern AI, which is based on all neural networks and stuff, hit a consumer moment with the introduction of ChatGPT. Obviously, because when people started saying, we all heard about AI, pattern recognition, data matching, being able to, just tell a cat from a dog and a human, that kind of stuff. But I think when people started playing with, an interface that was so intelligent, it was like you're talking to a human being. Is there a quantum computing moment of that kind? You think that we may expand into the consumer realm?
So maybe not. I don't see it at that level of like that consumer touch point. But one area that I think we will see this analogous to was the uptake of GPUs. And if everyone recalls, GPUs first were for graphics, vectors, types of calculations. But then people started finding that it was really useful for scientific compute. And people were using it to do their research. The fun thing about where we are today with the machines that we're building at the scale of 100 qubits plus is it's already beyond what you can simulate classically for certain kinds of circuits. And what that means is now it can be used as a tool for potentially heuristic advantage. There's this period of exploration where we're super excited about right now, where it's not necessarily advantages or algorithms that are written down pen and paper, but there's tremendous potential for users to leverage it in combination with other compute resources to now start finding advantages in either an economic way or in an accuracy way or an efficiency way, where we'll find that gap and it starts to really, have an uptake in terms of how it is used for scientific compute.
I see. Excellent, wonderful. Is quantum computing a race like the media makes it out to be, or are all of you guys collaborating with each other and sharing research and developments and building upon? I mean, for example, in the AI, a lot of AI is open source. The moment DeepSeek comes out, they throw it into the open source or whatever. XYZ, Meta, everybody just says, this is the latest research, we want the community to benefit from it. Is there that kind of collaboration in quantum computing, or is it a race?
I think it's a little bit of both, to be honest with you. I mean, all of our companies publish, in the academic literature. There's lots of great things happening at universities around the world. There are, we at Microsoft do collaborate with a number of companies. We collaborate fairly deeply with Atom Computing, a startup based in Boulder, two startups based in Boulder, Atom Computing and Quantinuum, which respectively neutral atom and ion-based quantum computers. And we certainly are open to collaborating with other companies. So there are aspects of, we understand that it's such a difficult problem that, building on, learning with, and partnering with other companies makes a lot of sense. There are also things that we do that, are proprietary, that we keep to ourselves, that we think is some of our secret sauce, and, to the extent that it's a race, we think, it's to our benefit. So it's a little bit of both.
If I can weigh in, I've been in a few deep tech industries, including autonomous driving. It is a race, and I'm not going to sugarcoat it. And look, largely when dynamics settle, there will be like one or two gorillas, a few chimps, and a few monkeys in the room when you're using Jeffrey Moore's analogy. And this industry is no different, except that the time horizon is longer.
Yeah. So, is there a common architecture and understanding, or is that also completely different? Like, what is quantum computing? We use XYZ circuitry, you use something else. We all know the end result is some form of supercomputing, but we'll use our own techniques and you use your own.
So we've been very, we've been upfront about putting things out there, and also at a certain level, open source in the both, right? So I mentioned before, we first put systems on the cloud 9 years ago. Then the year after they came out, we introduced Qiskit, which is our open source software development kit. Arvin and his team, Q-Control, they actually develop on Qiskit. So there's API layer, and then there's areas where actually third parties are encouraged to build into the full ecosystem, right? Because to us, and also from a particular layer, it doesn't matter what hardware you actually drive to, you can all speak the same language of quantum circuits, right? Then it really becomes, abstractions to the levels of applications and domain-specific applications, and you start to think about, the other modern software stacks in terms of building out compute libraries and so forth.
Yeah, and the other framework to think about it is there are some architectures that are relatively proven, like superconducting, what IBM uses and such, and then there are some that are experimental, like neutral atoms that these guys have invested in, etc. We are curious to see how they'll perform when they come out, and then there are also certain architectures that are out there for the future. There are some that are trying to build the perfect qubit. Yeah, so no noise, perfect qubit, and I build one, I can build a million, I can build a billion, and and Microsoft has been looking at that as well as some other groups around the world as well. So it's like a risk portfolio, right? You either work with what's known or you work with the unknown, but it's a longer payoff, but it's also probably it's bigger. The other framework to look at it if you're an investor or a VC is look at which architecture scale, and as you get deeper and deeper into this sector, you'll understand that certain architectures have architectural challenges. For example, they may need an architectural pivot in order to be able to go from 100 qubits to 1,000 to a million. So all of these are things to sort of look into.
Listen, thank you so much, Jerry, Arvind, and Chetan, and give a big round of applause to heavyweights of quantum computing. Thank you all.
Thank you.